how big is the universe? You'd think that'd be a simple question, right? Something astronomers would have, pinned down by now.
Well, it sounds simple, but honestly, it's one of those questions that still gives everyone pause, even the experts.
Yeah, it reminds me a bit of like Darwinian evolution. We get the core idea, it's fundamental, but the actual implications,
Yeah.
people are still debating those.
Absolutely. And speaking of fundamentals, it was 40 years ago, this July, wasn't it, that the cosmic microwave background discovery really cemented the idea of the expanding universe.
That's right. It's like the bedrock of cosmology now. But just like evolution, those implications, especially about expansion, they get misunderstood
Hmm.
a lot.
Uh-huh. And those misunderstandings really hit at the core of the whole Big Bang model.
So that's what we're digging into today, trying to clear up some of that confusion.
Exactly. We've pulled together some really great sources for this deep dive university articles from UBC, BBC Sky at Night Magazine, Live Science, Space.com, even some Reddit threads, and a blog post by Sean Carroll.
Quite the mix.
Yeah, a good range. And our goal really is to unpack this whole size question. What does expansion actually mean? What's it expanding into? And the big one is everything in it expanding too, like us.
Okay, let's start with maybe the biggest misconception, the Big Bang. People picture like a bomb, right? An explosion from one point out into empty space.
That image is so common, but it's wrong. The key thing, and UBC mentions this, is it wasn't an explosion in space.
Ah,
It was an explosion of space. Think about the surface of a balloon being inflated.
okay.
Every point on that surface is moving away from every other point. There's no single center on the surface where the expansion started. It's happening everywhere.
So the Big Bang happened right here, where I'm sitting.
And where I'm sitting, and everywhere else, simultaneously. It wasn't like a conventional bomb with a blast center driven by pressure. It was space itself stretching.
Okay, I like the balloon analogy, but it kind of breaks down too, doesn't it?
Mm.
Because we see the balloon expanding into our 3D room.
That's its limitation, exactly. The 2D surface needs our 3D space. But according to Einstein's general relativity, our 3D space doesn't need some extra higher dimension to expand into.
It just expands on its own.
Pretty much. Space itself is dynamic. It can stretch, shrink, curve, all intrinsically. There's no outside it needs to expand into. It's the fabric itself changing.
Okay, but then what about when scientists say the early universe was the size of a grapefruit? How does that fit if the Big Bang was everywhere?
Right, that causes confusion too. What they mean is the observable universe, the part we can currently see, looking back almost 13.8 billion years.
Okay.
If you run the clock backwards on that specific region's expansion, it was incredibly dense and hot and compressed into a volume roughly the size of a grapefruit very early on.
Ah, so it's just our patch, round back, not the entire universe.
Precisely. The entire universe might have been infinite even then. The grapefruit refers to the observable bit's past state, not some initial tiny nugget the whole thing grew from.
Got it. So back to this expanding into question. If it doesn't need a higher dimension, is there anything beyond the universe?
Well, within general relativity, the concept of beyond the universe as a whole doesn't really make sense. The universe is kind of by definition all there is spatially.
So asking what's beyond it is like asking what's north of the North Pole.
That's a great analogy for it, yeah. The question itself doesn't quite fit the framework.
Okay. Let's shift gears. Woody Allen worried about this in Annie Hall, right? If the universe is expanding, are we expanding? Is Brooklyn expanding?
Ha! Yes, the classic Annie Hall worry. And the short answer is no, thankfully. At least not because of the universe's expansion itself.
Why not, if space is stretching?
Because a steady coasting expansion doesn't really exert a force to make things grow. Think about us, or the Earth, or even an atom. Our size is determined by internal forces holding us together, electromagnetism for atoms, gravity for planets and stars.
So those local forces are much stronger.
Way stronger on those scales. They easily overpower the gentle stretching of space. We're bound systems. Space expands between us and distant galaxies, but it doesn't stretch the ruler you're holding or the atoms in your body.
What if the expansion wasn't steady, though? What about accelerated expansion, dark energy? Does that create a force?
Good question. Yes, accelerated expansion does introduce a kind of outward push, but even that doesn't make bound objects continuously expand.
No.
No. As Sean Carroll explains in his post, if gravity suddenly got stronger, you'd get slightly compressed until you reached a new, smaller equilibrium size. You wouldn't just keep shrinking forever. Similarly, accelerated expansion might slightly adjust the equilibrium size of, say, galaxy clusters over vast timescales, but it won't rip apart atoms or cities. They just settle into a new balance, if anything.
Okay, that's reassuring. We're not going to suddenly stretch apart.
Yeah.
But you mentioned light earlier. Photons do get stretched. Their wavelengths expand.
Yes, they do. And that's a really key difference. Photons aren't like us, or planets, held together by internal forces in the same way. A photon's wavelength is fundamentally sort of imprinted on the space it travels through, as that space expands during the photon's journey across the cosmos.
The wavelength stretches with it.
Exactly. If the universe doubles in size while a photon is traveling, its wavelength doubles too. And that is the primary cause of what we see as cosmic redshift.
Ah, okay. So that leads us nicely to the size of what we can actually see, the observable universe. What is that boundary?
Right, so the Big Bang happened about 13.8 billion years ago. Light travels at a finite speed, so we can only see things whose light has had time to reach us since then.
Makes sense. Like a horizon.
Precisely. It's called the cosmological horizon. But because space itself has been expanding the whole time that light was traveling,
The edge is further away than 13.8 billion light years.
much further. The current distance, what we call the co-moving distance to that edge, is estimated to be about 46.5 billion light years in every direction.
46 billion. Wow. So diameter of what, 93 billion light years?
That's the one. About 93 billion light years across. It's a staggering volume.
And just to be clear, that 46.5 billion light year distance, that's where those things are now.
Yes, that's their current distance, accounting for all the expansion that happened while their light traveled to us. When the light we see left those most distant objects, they were much, much closer.
Like the CMB, the cosmic microwave background.
Exactly. The matter that emitted the CMB light we detect today, that light started its journey only about 380,000 years after the Big Bang. That matter is now about 46 billion light years away from us.
But back then,
Back then, it was only about 42 million light years away. That huge difference really shows you how much space is stretched.
incredible. Okay, is that 93 billion light year bubble the entire universe then? Or just our observable patch?
That's the critical question. It's just the patch we can currently observe. The entire universe could be vastly larger.
Or even infinite?
Or even infinite. We have no evidence suggesting our observable horizon is a real physical edge. It's just an edge in time and light travel for us.
Our BBC source mentioned finite but unbounded, like a sphere.
Yeah, that's a possibility some models consider like a 3D version of the balloon's surface. Finite volume, but no edge to fall off. However, the current evidence actually points very strongly towards the universe being geometrically flat.
Flat, like a sheet of paper.
Geometrically speaking, yes. And if it's flat and extends beyond our observable horizon, the simplest assumption is that it just keeps going. Possibly forever.
Which means the whole universe might genuinely be infinite. Mind-blowing.
It's a lot to take in.
Okay, this leads to another mind bender. If things are getting carried away by expanding space, can they recede from us faster than the speed of light? Doesn't that break Einstein's rule?
The faster than light recession. This trips so many people up. And yes, according to Hubble's law, which says recession speed is proportional to distance, UHD, if you look far enough away.
The speed gets bigger and bigger.
Until eventually, beyond a certain distance called the Hubble distance, the calculated recession speed does exceed the speed of light.
Why, Einstein? Special relativity. See.
Right. But here's the crucial distinction, again, from general relativity. Special relativity limits how fast things can move through space.
Okay.
The recession of distant galaxies isn't them rocketing through space faster than light. It's the space between us and them expanding extremely rapidly.
Like points on that balloon moving apart faster than an ant could crawl between them, just
Oh.
because the rubber is stretching fast.
Exactly that analogy. The expansion of space is a general relativistic effect, not bound by special relativity's speed limit for motion within space. Locally, nothing can outpace light. But space itself can stretch in a way that separates distant objects faster than light could cross that growing gap.
So it doesn't violate relativity. That's wild.
It feels counterintuitive,
Yeah.
but it's consistent within the framework of general relativity.
Okay, that distinction, motion through space versus expansion of space, is absolutely fundamental.
It really is. And it's also why we see that cosmic redshift we talked about.
Right, the stretching of light waves. Is it only that stretching? Or is there also a normal Doppler effect, like a siren moving away?
Good question. For nearby galaxies, their actual motion through space does contribute a standard Doppler shift. But for the really distant stuff,
Yeah.
the dominant effect by far is the cosmological redshift, the stretching of the light waves by the expansion of space during their long journey. As our UBC source notes, astronomers sometimes confusingly call it all Doppler shift, but the underlying physics and the formulas are different, especially at vast distances.
So the stretching is the main story for distant galaxies.
Definitely. And get this. Based on the standard model, galaxies with a measured redshift of about 1.5 are already receding from us at the speed of light due to expansion.
And we see things with higher redshifts than
Oh,
that.
yeah. Thousands of them, meaning we routinely observe galaxies that are currently receding from us faster than light. Even the plasma that emitted the CMB was receding at something like 50 times the speed of light back then.
Wait. If they're receding faster than light, how can we see them? Shouldn't their light never be able to reach us?
Ah, another fantastic puzzle. You'd think the light would just get dragged away, right? But remember, the Hubble distance, that distance beyond which things recede faster than light, it's not fixed.
Yeah.
The Hubble distance itself changes over cosmic time. Generally, it's been increasing. So imagine a photon emitted from a superluminally receding galaxy. Initially, it might be fighting a losing battle, getting carried further away.
Right, like swimming against a really strong current.
Exactly. But if the region of space the photon is in eventually expands slower relative to us, or if the Hubble distance grows to encompass the photon's location.
The current slows down enough for the swimmer.
Precisely. The photon can eventually cross into a region where space is expanding slower than light relative to us, and then it can start making progress towards Earth.
So the light can eventually reach us, even if the galaxy itself is still receding faster than light when we see the light.
That's right. The galaxy might still be moving away superluminally today, but the light it emitted billions of years ago can complete its journey. It means the Hubble distance isn't the edge of the observable universe. The real edge is set by light travel time since the Big Bang.
This is just layers upon layers of weirdness. It completely breaks our everyday intuition. I saw some analogies in the sources trying to help grasp the scale. Any good ones?
The Reddit threads had some fun ones. I liked the one shrinking the solar system to a quarter. On that scale, the Milky Way becomes the size of the USA and like 35 kilometers thick.
Wow. That emphasizes the galaxy scale. What about the emptiness?
There was the one about fitting all the other planets between the Earth and the Moon. It really drives home how much empty space there is, even locally.
That one always gets me. It feels like it should be packed, but it's mostly void.
Totally.
Yeah.
And then going the other way, comparing an atom's nucleus to a fly in a huge sports arena representing the electron cloud,
Yeah.
or the Planck volume to an atom being like an atom to the entire observable universe. The range of scales is just immense.
Almost impossible to really wrap your head around. Now, Sean Carroll's post asked a great question. Why is the universe so damn big? What was his take?
He points out this huge discrepancy between the cosmic scale, billions of light years, 129 centimeters, and the fundamental scales of physics, like the Planck length, 1033 centimeters, or even atomic size, 10 to 8 centimeters.
Right, it seems excessive.
His suggestion, partly, is that maybe bigness and emptiness are just the most statistically likely states for stuff, given general relativity where space itself is dynamic. For any amount of energy and matter, there are vastly more ways for it to be spread out thinly over a huge volume than packed densely. High entropy states tend to be big and sparse.
So maybe it's big because being big and empty is just the default, the most probable arrangement.
That's part of the idea, but he also connects it to the huge mysteries around the cosmological constant point, the energy of empty space driving accelerated expansion.
The thing causing all the trouble.
Pretty much. There's the coincidence problem. Why is its energy scale weirdly similar to the universe's matter density today? And the deeper cosmological constant problem. Why is its value so incredibly absurdly tiny compared to what particle physics predicts it should be, like 120 orders of magnitude smaller?
And we have no idea why.
No widely accepted answer. Carroll muses that maybe the universe is big because the cosmological constant is small, allowing structures to form over billions of years before expansion took over completely. But that just pushes the question back. Why is it so small?
It always comes back to more questions.
Yeah.
He also mentioned the sheer number of particles, didn't he? Even though it's mostly empty, there's still a lot of stuff.
Yeah, trillions upon trillions of stars, countless photons and neutrinos. He points out that from an entropy perspective, a much emptier universe might be more natural. The fact that our early universe started in such a low entropy, high density state packed with particles is another fundamental puzzle we haven't solved. It's tied into the arrow of time and why the universe isn't just a uniform, boring soup.
So the size, the emptiness, the amount of stuff, the expansion, it's all interconnected with these really deep unanswered questions about the universe's initial state and fundamental laws.
Exactly. They're all pieces of the same grand puzzle.
Okay, so let's circle back one last time to the edge question. We know the observable universe has a horizon, an apparent edge, but the universe as a whole, does it have a real edge?
Right. As we touched on, based on current evidence suggesting a flat geometry,
Like that infinite sheet of paper.
if it is indeed flat and extends infinitely, then no, there's no edge. It just keeps going. The concept of an edge doesn't really apply to an infinite space.
Even if it were finite but unbounded, like
Yeah.
that 3D sphere surface,
Yeah.
still no edge you could fall off, right?
Correct. You'd eventually just loop back around, hypothetically. So, in the most plausible scenarios, based on current data, either flat and infinite or finite and positively curved, there isn't a physical boundary or edge to the universe itself.
Wow, okay. This has been quite the journey through space and time. Let's try and sum up the big takeaways.
Okay, deep breath. First, the Big Bang wasn't an explosion in space, but of space, happening everywhere.
Right. And the universe expands intrinsically, doesn't need anything to expand into.
Correct. And while space expands, bound objects like us, planets, atoms, they don't expand with it because local forces hold them together.
But light waves do stretch, causing cosmological redshift.
Yes, the observable universe is huge, about 93 billion light years across, but that's just the part light has had time to reach us from. The whole universe, unknown, could be infinite.
And galaxies can recede faster than light due to the expansion of space without breaking Einstein's rules about speed through space.
You got it. And that faster than light recession doesn't prevent us from eventually seeing their light because the Hubble distance changes.
Yeah, okay. It really does challenge everything you think you know about space.
Absolutely. Thinking about an infinite universe or one that loops back on itself, it fundamentally shifts your perspective on our place in the cosmos.
It makes you wonder what else is out there beyond what we can currently see and what fundamental laws dictate this incredible scale.
Exactly. What are the ultimate limits of our knowledge? Given these vast distances and times, what new physics might we need to truly understand the universe's origin and ultimate fate? So many questions left.
Definitely leaves you with a lot to chew on. If this has sparked your curiosity, we really recommend checking out the sources we mentioned. They offer even more detail. Keep exploring cosmology.
Thanks for diving deep with us today.